Okay, I think we are live.
Okay, then let's begin.
Mhm.
So welcome everyone to this workshop. My name is Marcelo, and I'm from Uruguay. And
And my name is Christian, and I'm from Germany.
so we are excited to give the first workshop about JuliaReach, which is our software stack um, to work on some problem that is called reachability analysis. And for those of you who are not familiar with this topic, this workshop is going to introduce all the details, like starting from scratch until we consider more complex scenarios. And for those of you who don't know about JuliaReach, well, this is a project that we began in around 2019, and then we have continued to create these packages that are open source and that show all our different research projects with among different groups. So to just give you a very quick idea, in this first few minutes, I'm going to give you an overview of things that we are going to present, and then we will go into more details about the packages in trying to give you lots of examples so you can see what it's all about. So, I mean, there are essentially three big aspects of that we will be considering today. So the first one is a verification of system safety. So this means that we have models and we have some requirements that have to be met. And in many applications, one is interested in to ensure that the system is safe under some conditions. So we will see that if you take a model which has millions and millions of corner cases, this alternative set propagation approach will let you analyze all those corner cases in simultaneous with only one computation and in less than 1 second. And this is because how these methods actually work, and we will try to bring you down to earth how are these methods actually, what they are doing and what things you can do with them. So then the second aspect is about dynamical systems, which are considered to be hybrid, meaning that you have complex interactions of events and differential equations, and we will show examples of set propagation techniques applied to such problems. And finally, we will also discuss about ongoing research work and mixing. One side is dynamical systems, and on the other side are neural networks, in order to assess robustness of neural network control systems using these tools. So, well, the domain of reachability analysis is being applied in several areas, from safety verification and autonomous vehicles to validation of control strategies to verification of deep neural networks, controller synthesis. So while we will not enter into all of these details, we will try to give you some general ideas. And I should also advertise, right, that there will be a mini symposium at JuliaCon this week. And this mini symposium is going to include talks from different groups, building on global optimization techniques, probabilistic systems, cyber physical systems. So you shouldn't miss this talk, which will feature an invited talk by Professor Goran Fres about set propagation for verifying safe behavior in cyber physical systems. Okay, so here are, if I want to summarize, for those of you who will follow this talk, what you will learn. So how is this set-based approach to modeling and simulations related to the traditional simulation-based approach? We will also show you examples of how to code set-based algorithms that combine symbolics and numerics using our tools. We will also discuss techniques for reachability of linear differential equations under under uncertainties which can be non-deterministic. And then we will also show examples of how to use these tools for nonlinear differential equations using a method called Taylor model methods. And then we will conclude with some aspects about hybrid systems and the deep neural networks. So it contains lots of stuff, but don't feel scared if you're not familiar with these topics. This workshop is for you, so stay with us. We have prepared material that starts from the ground up. We have prepared material that can be followed by those who have an undergraduate level of calculus and differential equations. And even if you've taken these materials since a long time, we will review everything that's required in different steps of the presentation. Okay, so to summarize, this workshop has mainly three big parts. So the first part that will be presented by Christian, we will present our tool symbolic numeric computations called lazy sets. Then on the second part, we will present, I will present the set propagation method, like what it means and how do you compute with this using reachability analysis tools. And then we will also discuss, for instance, nonlinear differential equations as well. We will see that standard integrations with the sets which are, for instance, distributed in space just do not provide helpful solutions. You have to write specialized methods for these solutions to actually converge and give results like those which we will show. And then finally, we will present an application to neural network control systems. So to conclude this introduction here, so well, this work would not be possible if it weren't for a team of researchers, a team of students that I mentioned here: Luis Bennett, Daniel Freire, Ander Gray, Sebastiana, Nuciel, and Adesh, who all of those who were part of previous Julia Summer of Code and Julia Seasons of Code summers. So it's been part of the Julia community as well. Jorge Perez, David Sanders are also present in our research groups, and I also want to thank Benoit Lega and Julie Wechsler for their support in different contributions on the Julia ecosystem. So I'm ready regarding this introduction. You can also send us a question through. There are also questions and there are materials that are available. So whenever you want to.
Okay, thanks, Marcelo. So I'll switch to the other notebook, and I will start with the presentation on lazy sets. So if you want to follow, this is the package that you need, and these are the packages that you need for this notebook. But I will actually not do much interaction to save time. So you can basically just follow what I show here. So this presentation will actually be quite long. So we'll target 90 minutes because this is the basic of everything that we will show later. Yeah, and it's good to have that, to bring that to you. So what is lazy sets? Lazy sets is a library for set computations. And whenever we say set in this workshop, we mean set of points in a Euclidean space or just vectors. And in this presentation, we will usually show two-dimensional sets just because you can easily plot them, but of course, everything generalizes. So before we go into the details, let's just start with some simple motivation. So we have these 3 points, 1, 1, 3, 1, and 2, 3. In Julia, of course, you can just define them as vectors. And then using lazy sets, you can just wrap them in so-called singletons. These are just sets containing exactly 1 point. And then you can plot them. I didn't say I defined P as a shorthand for a plot with some arguments. So just don't get confused. So P is just plot these 3 singletons. And yeah, not very exciting yet. And of course, you can plot hundreds of points like this, but how can you plot infinitely many points? That's not really possible. And a mathematician would say, well, you can represent infinitely many points as a set using set comprehension. And it is one goal of lazy sets to be able to do something similar, so represent a whole set of points elegantly. So just to give you some examples, mathematically you could write down the line segment between these 2 points like this. And in lazy sets you can just define line segment of these 2 endpoints, and then you have this infinite set of points here. Of course, you can also do this for all 3 possible line segments here. Then you can do the whole polygon area between these 3 points. This is just, you just write the polygon of these 3 points. Yeah, we can also plot so-called half spaces. So if you think the line x2 is 3 minus x1, then you can say everything that is below this line, including that line, is just a set of points x1, x2, where x1 plus x2 is less than or equal to 3. And in lazy sets, you can just write this as half space of 1 and 3. 1 is the factor here. So this set is actually unbounded. We just only plot this part. Yeah, and you can, of course, do operations between these sets. So you can take this triangle from before and then this half space and intersect them. And in lazy sets, you can just do intersection of these 2 sets, and then you get this green intersection here. Okay, so this is just really an appetizer. So what we need is set primitives to, like, for instance, this triangle or this half space, and then later we need set operations to create more complex sets. And we will start with the set primitives now in this next section here. So first I should settle the focus of lazy sets. So we consider mostly closed and convex sets. So what is a closed set? This is easy to describe with an example. If you consider this interval from 1 to 2, including the endpoints, then you can also write this as the set of points x, such that x is between 1 and 2 with non-strict inequalities here. This is a closed set because it contains the boundary points, while this is a non-closed set because the 1 is not included here. We have this strict inequality. And we don't support this in lazy sets. The other restriction is not a strict restriction, but it's how lazy sets started. So it started as a library for convex sets, and you can still see this because we have, I would say, very good support for convex sets, but not so good support for non-convex sets yet. And what is a convex set? This is again best described with an example. So consider this blue pentagon. A set is convex if you can pick any 2 points from the set and then take the line segment between these 2 points. And if this line segment is fully contained, and if this is true for all points, then the set is convex. So it's not hard to see that this pentagon is convex and that the square is convex. But of course, the union of these 2 sets is not convex because, yeah, taking these 2 random points here and drawing the line segment, it's clear that this line segment is not contained in the union. So yeah, so we restrict ourselves to convex sets mostly, and in this presentation, I think completely. Okay, here's another example. So in this example above, it was clear you can pick any 2 points and it will violate this condition about the line segment. Here's an example where the union of these 2 blue triangles is not convex, but there are examples where the line segment is contained. But of course, there's still at least one counterexample. All right, so next I want to discuss the symbolic representation of sets. Or actually, I think I will skip this, and if you want, you can read this up later. So the main idea is that you could, in principle, write in Julia a predicate representing a set like this, and this is we wouldn't need any external package for that. But with this predicate, you can only access this set or predicate via a membership query. You can ask, is a point in the set or not? But this is not super helpful if you want to do operations with these predicates. You could take the intersection with an and, but that's basically it. So we want to do something else or something more complex. That's why we need really new types for representing these sets. So now we will start with the basic set types that we have in lazy sets. So in a sense, most basic set type is the half space that we have already seen. So it's a set of points x such that a vector a transpose times x is less than or equal to b. So you can think like this. You have this hyperplane in general. In 2D, it's a line, and this normal vector a. And then you use the b to describe how far you move this line, in this case to the top right or bottom left. And this then describes the set of points that satisfy this inequality. Yeah, so this is very easy to write down, right? You just pass a vector and a scalar and you have it. And why is this so important? I will come to that. But first I wanted to say, you can also, if you prefer, use symbolics to write down this half space in a maybe more mathematical way. So you could define variables x and y, and then really the way you would write it down as a set, you can write it here. So you can say x plus y less than or equal to 2, and this is will give you exactly the same result. And in lazy sets, we can even check that these sets are equivalent, mathematically equivalent, so they represent the same set of points. So this result is true, which is in this case not really surprising because you actually have exactly the same internal representation, but this would also work for non-equal representations, of course. Yeah, so why is this half space important? In principle, you can represent any convex set as an intersection of half spaces, but in general, you would need infinitely many of them, and of course, we cannot do this. But still, it's a very useful set representation, but we need more to do to represent more interesting sets, of course. So we already saw the singleton. I will not say too much because it's actually very boring. You just pass a single point to it, and then it represents the set containing this single point. What is more interesting is the p-norm balls. So the set of points x such that given the center c, the distance of x to c is less than some radius r. So here are some examples. If you pick and the distance is in some norm. So let's pick the one norm. And if this is the center and the radius is 1, then you get this diamond here. If you increase the norm, the edges turn to the outside. Then for the norm 2, you get the Euclidean ball. And if you let p go to infinity, then it becomes a square. And this are actually the only p-norm balls with actual corners, and the others are round. So yeah, you can represent all of these with lazy sets. For this, and this special case, we have dedicated set types, ball in, ball 2, and ball 1. And for everything else, you can use this ball p, where you additionally pass the p. And this is useful, for instance, to define a neighborhood around a point. And something I should really mention is that when you define these sets, there's no computation going on. It's really just wrapping it into a new object. So when you do ball p with these arguments, it takes no time. It's just the allocations for allocating this vector and the new object, and that's it. And also internally, it just really stores this information. Of course, when you plot these sets, then it triggers some computations in the background, but we will come to this later. So this is also nice if you want to define some really complex sets. So let's say we define a hypercube, so and ball in the infinity norm is a hypercube in 1000 dimensions. And if you know that a hypercube in n dimensions has 2 to the power of n vertices, that would be prohibitively large if you wanted to describe it with as a set of vertices. But you can really just do it like this, and it takes no time, right? Of course, if I now wanted to ask for the vertices of the set, we wouldn't be able to stop today. All right, so this is the basics. We have many more set types to represent sets, but for now, this is sufficient. And I want to go to the operations. We will come back to this later. So assume you have some basic set types and you're happy with that, but the possibilities are not that big. So we also want to be able to apply operations. We will actually see this in the other parts of the workshop that in possible applications. So the typical operations you want to do to sets is translation, Minkowski sum, linear map, affine map, convex hull, intersection, Cartesian product. We will come to that later. So the nice property of convex sets is that they are actually closed under all of these operations, which means that if you take an arbitrary number of convex sets and you apply some of these operations in an arbitrary order, you will always receive a convex set again. And yeah, so this is nice because we don't need any external tools at any time. But this is also only half true. We will also see some limits there. But for now, this is nice. And there's also another robust subclass of convex sets, and these are called convex polyhedra. We will also see them later. These are just intersections of finitely many half spaces, or also convex polytopes. These are additionally bounded polyhedra, and they have the same property that if you apply these operations, then you will not leave this class of sets. And this is actually very common in many sciences to use polyhedra. Okay, so now I will go through these operations to give you an idea. So a translation of a set by a vector is really just shifting the set or each element in the set by this vector. So I will just show you the plots. If this is the vector by which we want to shift, then you can think of this arrow vector here, and we really apply this arrow to all infinitely many points in the set. But of course, we don't do this in practice. We just shift the whole set. The next operation is a bit more tricky. The Minkowski sum, actually, mathematically, it's very easy. It's really just a pairwise sum of all the elements in X and Y. But it's harder to imagine what is going on there. A simple case is when one of the sets is a singleton, because then it's really just a translation. So you can say Minkowski sum of X and the singleton around some vector V. And then we can ask, is this equivalent to the thing that we did above with the translate? And the answer is yes. Then, of course, you can do more complex, add two more complex sets together. For instance, here we take a ball in the infinity norm, so a square centered in the origin, and we add it to this diamond, and this has the effect that we bloat this diamond. So you can think of it as at each point of the set, we draw this square around it. And then this is the shape that you get. This is still not so difficult, but then, yeah, in general, at least I find it difficult to compute in your head what will be the result. So if you take the sum of these two triangles, you will get this shape. You can think about it, and then at some point you will agree that this is correct, but I wouldn't have predicted that. But of course, lazy sets doesn't have to think, it just does some computations, and then you get this. Okay, next operation is the linear map. So given a matrix M with appropriate dimensions, you can multiply m to the set, which means you multiply it with every element again. So here's an example with the square, and m is the matrix given here. And then you get this. So by the linear map, you can rotate and shift and stretch sets. What you can also do is project. So if your matrix removes some dimensions, then you lose them, and then it's a projection, and this is useful for plotting high-dimensional sets. We even have a dedicated method for that project. So you can pass the set and the dimensions that you want to receive. And this is the same as doing the linear map with this matrix that eliminates the second dimension in this case. So let's give an example. If we have this two-dimensional set and we project it to 1D, then we get this interval and this interval. I did some tricks to actually plot this interval vertically here, because by default we plot one-dimensional sets on the x-axis. But it really gives you this interval, so this one-dimensional set. The affine map is actually just the sequence of a linear map and a translation. So, but this comes up in many applications, so it's useful to have its own function for that. But it's there's nothing new here. It's really just first doing the linear map and then doing the translation of that set again. More interesting is the convex hull. So given a set of points, not necessarily convex, the convex hull gives you the smallest set that contains X and is convex. So of course, for a convex set, it gives you the identity, but for a non-convex set, it gives you something new. So let's say we have these three sets here from before. You can take the convex hull of Y and Z. Z is this one, so of green and purple. And then take the convex hull of X and that set. So it's like taking the convex hull of all three sets. And this gives you this blue set then. And then there's the intersection. This is also very important, but also very nasty operation, as we will see. So again, this is very easy to write down, right? It's just a set of points that are common to both sets. And there are two cases. Either the sets do not intersect, then the result is the empty set. Or they actually do intersect, and then you get, in this case, this triangle. So far, so good. This is not difficult, but we will see some limitations here later. And the last operation we want to discuss is the Cartesian product. So you have a set of points that are basically glued together from these lower dimensional sets. So if you do the inverse of the problem that we saw before, if you take this one-dimensional set and this one-dimensional set, take the Cartesian product, you get this rectangle again. All right, so this is okay. I should remove this banner. No,
it was removed. Thanks. For those of you who are asking what is these files, so they are, again, we remind you that all the material for this workshop, you can find it on JuliaReach.
I can show it.
.com/JuliaCon 2021. Over there is the link. So then you will find different notebooks. This notebook is the one lazy sets.
Mm-hmm. Okay. So right. So I already said that one important class of sets is the polyhedral computations, or the set of polyhedra. And for that, we rely on the polyhedra library. And we also use this gives you a very convenient way to work with polyhedra, and they have two different possible representations. Either you can describe the half spaces. This is the hrep or you can describe the vertices and rays. This is the VREP, and Polyhedra hides all these details from you, so it will just do the computations whenever needed. And CDDlib is a library for this for efficient and robust computations with this double description, and we use that in many cases as our default solver. In lasers, we don't have these unbounded VREP sets. I just want to mention this, and we have some wrapper types around the polyhedra types. So we have an H polyhedron for these unbounded polyhedra and HREP, and H polytope and V polytope for the bounded case. So these two are really just the same. This one just additionally encodes the fact that it is bounded, which is useful in many operations to know, but expensive to compute in general, or at least not completely cheap. Yeah, we can convert between these two dual descriptions with 2 HREP and 2 VREP. So here we define a V polytope. So this is really just the generalization of the polygon that we saw before to arbitrary dimensions. So you pass the list of vertices, and the H polytope has a list of half spaces, and in this case they are equivalent. So, and here I also convert them with these helper functions. So here's a plot. So to describe this triangle as a polyhedron, or indeed a polytope because it's bounded, you can either pass these 3 vertices or these 3 half spaces that are bounded by these 3 red lines, and the intersections then exactly the same. This is, of course, a coincidence that we have 3 vertices and 3 half spaces here. In general, these numbers do not coincide. So sometimes it's better to use the vertex representation, sometimes it's better to use the half space representation. And for certain operations, you really have to convert to the other. And sometimes this can yield an exponential blow up, and that's why we try to avoid this if possible, but in general, you cannot avoid it. Yeah, so here's another example of a 3-dimensional set this time. So this is really just 6 half spaces defining the cube here. You only see a projection here, of course. And then a polytope with 3 vertices. The origin, the 3, 3 vertex, and this vertex, which is 1, 2, 3. And then if you do the intersection, we can then plot the projections in, for instance, 1 and 3. I can also change this, of course. And then it gives you something else. This is maybe a bit surprising that you don't get this one, but this is because of the projection, so this might be misleading. All right. So the intersection of these two, if you go back, here we define a polyhedron, which could generally be unbounded. In this case, it is bounded, but we just don't say that. And this V polytope, which is really bounded by definition. If you take the intersection of a possibly unbounded set with a bounded set, you know that you get a bounded set in return. And that's why we return an H polytope, which encodes boundedness. And we can, of course, compute the constraints, so the half spaces, and also the vertices. So this internally would then go to this dual representation if it's not already computed. Yeah, so that's it for polyhedra. So all of this works, and we have this wrapper around the polyhedra library. Now I will briefly go into other set representations that we have. So a very basic one is the hyperrectangle. In lazy sets, you describe it as by defining the center point and the radius, which is also a vector. So in each dimension, you can have a different radius. In this case, this is the radius 1.5 in x1. And 0.5 in x2. Yeah, it's not really difficult, but it's a very general or very often applied in applications. For instance, if you start from a set, you usually start from some hyperrectangle because that's easy to describe. And yeah. So then the next sets I want to discuss are the polygons. So I already introduced polytopes, and polygons are just polytopes in 2 dimensions. So why do we need them? We actually don't need them in principle, but you can do some tricks in 2D that you cannot do in general. And that gives you a nice speed up in applications. And since 2D is so fundamental, for instance, if you want to plot, we convert to 2D. Or if you want to do toy examples that you can reason about, you usually do that in 2D. So yeah, 2D is very important, and that's why we have this special support for 2-dimensional sets.
Or if you want to decompose a high-dimensional system into 2-dimensional blocks and do this efficiently and then wrap up. So, yeah. But we will comment about that later.
Okay. All right, so here I create a random polygon in H representation with 30 constraints. And then I apply a linear map, which is similar but not the same. And then take the intersection and I time this. And then I get this, I convert these polygons to this H polytope type, which really has the same internal representation. It just has the list of constraints, but it doesn't know that things are in 2D. So it uses these general computations in arbitrary dimensions. And I again do the intersection. And then you see that you get something like, I don't know, 50 times faster, something like this. Runtime for doing the same operation just because you know this it's 2D and you can use some more efficient algorithms. Of course, we could check this, but then still there's something going on in the background with sorting the constraints in some order. So at the moment, at least, we don't do this. So if you know you are in 2D, you should create these polygons instead and then get this nice speed up for free. And you can see they are actually the same. Yes. Yeah. Marcelo?
No, and if you want even more speed up, there are lazy sets libraries built on generic arrays. So that's all you can know about some Julia code. So for instance, you can use static arrays in order to get even more speed up with stack allocator and more sophisticated array types. So.
Okay, here I do the same for the V polygon. Yeah, sometimes I have these issues with plotting. I don't know what to do against that. Sorry for that, but it will just look the same. So here create a random polygon with 5,000 vertices. Again, do this linear map and then compute the Minkowski sum. And then I convert to this V polytope type, do the same. And again, there's a large speed up if you do it in 2D. All right, so this is really just some advertising of these efficient computations in 2D. Then the next, and I think last very important set type that we have is the Zonotope. And I guess this is probably new to many people, so I will spend a bit more time here. So in general, you can think of a Zonotope as a linear map applied to a hypercube, but this is not really helpful, at least for me. So the internal representation of a Zonotope is you have a center point, and then you have a sum of vectors that you add, and the vectors are products of generators G and let's say normalization vectors psi, such that which come from this interval from -1 to 1. So I guess it's useful to have a picture here. So let's say we take the center 2, 2 here, and then we have this first vector G1, which is the vector 1, 0, and G2, which is the vector 0.5, 1. And you can see that these vectors basically span this set, and then you can multiply them with any number from -1 to 1. So that's also why we also go to the left and to the bottom here. And you can, by choosing appropriate factors, get to any point in this shape here. So it's clear from this definition that zonotopes are centrally symmetric, but in general, they do not coincide with centrally symmetric polytopes. In 2D, they do. So so far, it's not so clear why this is a good set representation, but the nice thing about zonotopes is that they are closed under Minkowski sum and linear map, which are very important operations in certain areas. And they are not just closed under these operations, but you can also really efficiently compute the result. So here's an example. I have some matrix. I apply the linear map to the zonotope, then I get a zonotope again. And here I compute the Minkowski sum of these previous two zonotopes, and I get another zonotope again. Yeah, just plotting them, but this doesn't make much sense. What you can see here is that the number of generators actually increases when you do the Minkowski sum. This is in general unavoidable. So that's also why these zonotopes look fairly simple, but then you get already some more complex shape after the Minkowski sum. Marcelo?
Yeah, and then we also have when the number of the complexity of the sets increases, and we have order reduction methods. I don't know if you at some point.
Yeah, I didn't show this here, but you. I can maybe quickly try. Sorry. Is it reduce order? I didn't do this in a while.
Yeah.
Oh, what is? Okay, sorry. I need to load the cell again.
So in some part of the workshop, we will do some live coding.
Yeah. So okay, this is it. This worked. I was lucky.
Yeah.
So I just plot this. Maybe I additionally plot the original. But this is a boring one, not. Okay, sorry. So now I took this more complex zonotope. Oh, it's really slow here. This more complex zonotope, this one, and I call this reduce order with the argument 1, which means I just want a zonotope with 1 generator per dimension. I think I skipped this part. Yeah, so the order of a zonotope is defined as the ratio of the number of generators and the dimension. So in this case, we are in 2D. So we allow at most 2 generators. And then a good approximation for that is the box. So if you pass 1, we always give you the box around it. But not sure if this makes sense. Try 3 generators. Okay, I think I shouldn't do too much coding. It's really slow here with all this video going on. Yeah, then you get some better approximation, which now would only have 3 generators. I didn't show the generators, but yeah, trust me. All right, so the interval is another simple set type. You can just pass so it's a 1-dimensional set, which is bounded from the left and from the right. You just pass the 2 boundary points. And actually, the interval in these sets is just a wrapper around the interval arithmetic interval. So you get all the nice properties like conservative rounding as well. All right, and then there are some maybe not so interesting set types. I will just briefly go through them. So we have the hyperplane or line. In 2D, it's a line. We have a specific type for 2D. It's really just defined in the same way as a half space, just that you don't have this less than or equal, but just the equal. So you pass A and B. Then we have the line segment. We already saw this at the very beginning. So you just pass the two endpoints, and then it represents this line segment between. The empty set seems boring, but sometimes it's useful to know that the set is empty without recomputing this information. And the last set I think that I have here is the parallelotope. This is just a more efficient representation of a set that really just has parallel sides like this. So you only have to store one of these constraints instead of two. Yeah, the plot is also a bit broken here. I forgot there's also the ellipsoid. So in 2D, this is called an ellipse, and in general, this is called an ellipsoid. You can represent this by a center, C, in this case, this would be C, and some so-called shape matrix, which has to be positive definite. And yeah, you can get these nice curvy shapes like this. They also have some nice properties. They are, I think, closed under linear maps, if I remember correctly. All right, so that's it for the concrete set representations. So for most of them, when you define them, there's no computation going on. Only for these polygon types, I think, there we sort the vertices or constraints for faster computations later on. But all the other set types really just wrap the inputs, and yeah, the definition is takes no time basically. But then when we want to do operations with these sets, it starts to get interesting, because sometimes I said at the beginning that convex sets are closed under all these operations that we saw, for instance, Minkowski sum. So in general, if you take two convex sets and compute their Minkowski sum, you get a convex set. And lazy sets is a library for convex sets, so you would hope that the result can be represented in lazy sets again. But this is not possible, because there are so many complex convex shapes that we, no matter how much we would work, you wouldn't be able to represent all of these sets effectively as one of these set types that we saw before. But there's a way around it. So if you, for instance, take this disk, so a Euclidean ball and a square, and you try to compute the Minkowski sum, this will fail. So I just hide this complex error message here, but we will not be able to do that, and this is because the shape is just well, very difficult to represent. But there's a way around it in lazy sets, and this is also where the name comes from. We just create a lazy wrapper object, in this case called Minkowski sum with capital letters here. So it's you define it in the same way. Instead of doing Minkowski sum in lowercase, you do Minkowski sum in uppercase. And that, again, takes no time, because it's just a new object that it creates that wraps x and y. So you can see it has two fields, x and y. The name is a coincidence here, but it's really just the same objects x and y from here. So again, no computations. So now at least we have some object in our hands that represents the result of the Minkowski sum of x and y. Of course, this doesn't help much, because if we want to do something with it, we still need to do this computation. But we will later see that this is actually, that we can do lots of things with this object without actually doing the concrete computation. So here's an example. How would it actually look like? So if you take this Euclidean ball from before and the square from before, and you computed the Minkowski sum, you would get this set. And of course, there is no set representation in lazy sets that can represent this complicated shape. But here we just plot this set Z, which is this lazy Minkowski sum. And this works fine. So something fancy is going on here, and we will see what is going on in a minute. But first, I want to say some convenience facts about these lazy set representations. So first, of course, we don't only have this for Minkowski sum, but for all the operations we saw before: the translation, linear map, affine map, convex hull, intersection, and Cartesian product. And you can nest them as deeply as you want. So you can create a convex hull of y and z, take the Minkowski sum with x, then translate this with this vector. This is what you would get. If you want to apply some of these operations, which are usually binary operations, to lots of sets at the same time, you don't have to do it like this. This deep nesting of Minkowski sums. You can just use the Minkowski sum array, which just receives a vector of sets and represents this this iterated application of this binary operation. But it doesn't do that actually in the background, but it's equivalent to that. And yeah, we have these convenience operations, operands, of course. So if you do the sum of two sets, you can also use this Unicode symbol for the Minkowski sum or just the normal plus. You will get the Minkowski sum, the lazy Minkowski sum. The reason why we don't give you the concrete Minkowski sum is exactly that that would fail in many cases, but this will always work. So yeah, you can do the plus with a vector, you can multiply a matrix with a set, do an affine map, the convex hull, the intersection, this is again a Unicode symbol, the Cartesian product, again a Unicode symbol. Yeah, and here just plotting work doesn't work. Now it works. Just to show that all of this works. So you get these lazy sets and we can plot them. And yeah, last but not least, there's also a function that takes a lazy set and tries to make it concrete again. So under the hood, if it sees a lazy Minkowski sum, it will just call the concrete Minkowski sum and do this iteratively. So if it's possible, this function will give you a concrete set representation in lazy sets, or it might fail. So in this case, if you do the lazy Minkowski sum of two squares, then of course you can do this concretely again, and it will give you this orange square. But for other, if one of these operands was a Euclidean ball, for instance, as above, it would fail. Okay, so this works really nicely for basically all of these operations, but one operation was missing, and this was the intersection. And yeah, I will come to this after this section, which explains basically the theory behind these lazy sets. So why does it actually work? Why can we actually work with these lazy sets compared to these non-working concrete set representations for these complicated shapes? So this will be a bit theoretical, but I will try to keep this theory to a minimum. So let's say we have a compact convex set. Compact means it's closed and bounded. It also generalizes to unbounded sets, but then you have to deal with infinities. So for now, let's just say we have bounded sets. The support function of a set X and a vector D, written like this, row of D and X, gives you a scalar, namely the maximum of the dot product of D and any point X in the set X. So this is the mathematical definition. I know this doesn't really say much. Just want to say in the literature, usually X is a subscript of rho so that it becomes a unary operation. So for those who know about the support function, this this is really the same. Before we see an example, let me also say that the points that maximize this expression, in general, they are not unique, so there might be multiple, even infinitely many of them. These points are called support vectors, and they are usually written with a sigma. So the intuitive explanation of the support function is that the support vectors are the extreme points of x in the direction d. So let me show this example maybe. We have this set x. Here's the origin, but just for your reference, if you ask for the direction d like this, then this would be the extreme point of x in this direction. If you go further in this direction, you will leave the set. And if you go, less in the direction of d, then you would be inside the set and you could still move on. So this is really, in this case, it's a unique extreme point or a unique support vector. If we had chosen this direction here, then all points on this edge would be support vectors. And the support function will give you now basically the b. If you remember the half space, this blue half space here consists of a normal vector a, which is d in this case, and a scalar b. And this number b is exactly the value of the support function. So it's not important that you understand this with these numbers, but what is important is that you understand that if you can compute the support function for a set, you can basically compute this half space that fully contains the set, but the tightest half space with that property. So this half space that is bounded here would not be interesting because you can get closer to x. And this half space here would also not be interesting because it doesn't fully contain x. And yeah, so with that, it's actually not such a big step to to do this in many directions now, right? Ask for the support function in multiple directions and use this to bound the set x in a finite number of directions. In this case, it's not very interesting because you already know x, but remember that we have these lazy sets and we don't really know how to compute these results in a concrete way. But if we have them as a lazy set and if we are somehow able to compute the support function for this lazy set, then we can evaluate the set in a choice of directions that we can make. And so we can get an arbitrarily close approximation of the set without actually computing it. Yeah, so in lazy sets, you write really row, or if you don't like Unicode, you can write support function and sigma or support vector. And here is basically the reason why the support function is so powerful. Can maybe zoom in a bit. That was not good. The reason is that the support function, how do you say that, is inductively or works inductively on this on the common set operations. So if you have a lazy scaling, we don't have that actually, but you can imitate this with a matrix. Then you can just pull out the scaling factor to the direction vector d, and you know how to scale a vector, right? This is very efficient and easy. But then you get the original set x here. So then if you know how to compute the support function of the original set x, you know how to do it for the scaling. Similarly, for the linear map, if you know how to do it for x, then by just transposing the matrix and multiplying with the direction, you know how to do it for the lazy linear map. The lazy Minkowski sum is just the sum of the results for each individual set. The convex hull, the result for the convex hull you get by taking the max of the results for x and y. For the Cartesian product, you just project the vector to the appropriate dimensions of x and y. So this is very easy. And it's very efficient as well. So you can really do this in high dimensions in no time. Marcelo?
Yep, we will see examples when we present the part on linear reachability.
Yeah. Yeah, I will not show applications in this notebook. We will do this later. But I will now explain what to do with this intersection, because I said we don't really know how to compute the support function of an intersection. So this is really missing in this list. And so there is some obvious heuristics. You can approximate this this is the result by just taking the min of the support function. So if you think, what is the support function of the intersection of this red and the blue disk, then of course it's the min of this half space and this half space. In this case, this is actually a good approximation because it will give you the exact solution, but it may also give you very coarse approximation. So here's another example where so by default, we don't use this heuristics in all cases. So in this case, I override the default in lazy sets to actually show you the result. If you take the approximation, for instance, in this direction, in the vertical direction, up to the upside, then for the blue set, you would get this half space bounded by this line, and for the red set, you would get the half space bounded by this line. So this heuristics would then give you this this small square here. And the reason why it cannot improve is if you wanted to add this direction going to the diagonal, then okay, I'm actually surprised now that I think about it. Why doesn't it work? Okay, sorry. I think I don't know why it actually doesn't work.
Did you plotted the box approximation of the intersection?
Yes. Okay. Yeah. Okay. Because I only use the okay. In this case, it's not very useful. So I plot the box approximation, but that is if you only use these directions, then this is actually the best you can get. But I forgot what I wanted to say here.
But using the direction normal to the side of the triangle, we would get an exact solution.
Yeah, indeed, yes. So I don't know again what I wanted to say here, but I think the next example is better. So here, if you have these two sets and clearly they don't intersect at all, if you use this approximation in this box directions, it would actually tell you, well, for this set you get this half space, for this set you get this half space, then the minimum is this bound, and similarly for the other three directions, and then you get, this is the approximation of the intersection, and it's true, right? This is an over approximation of the empty set, but it's a very coarse one. Okay, so there are other tricks to do the lazy intersection. So for instance, there's something based on optimization, some line search algorithm. We use the Optim package for that. So if you load this, you get this for free. So you can do the linear map of the what is this? I compute here the square and then the linear map, which is this set, like above. But then I compute the intersection, and it gives you the triangle that you would expect.
We have a question from the audience. Is this internally represented as an analytic or discrete geometry? So the lazy set representation.
What does it refer to? Sorry, maybe I read it too late. And
so I think it refers to whether what is represented when we call intersection, or what we call lazy intersection. So I would say it reflects the analytic or exact result that you would get, because as you were saying, when you say intersection of such and such set, then it's just a symbolic way of representing the operation. And only after you want to operate with it, you will, for instance, approximate with support functions and so on. Yeah.
Mm-hmm. Yeah, I agree. Yeah, and lastly, of course, for polyhedra, the intersection, you can do the intersection directly by accumulating the constraints. So for polyhedra, we would actually do this as well. Okay, so now some application of this support function. So if you have a set X, or a convex set X, then you can over-approximate it, so you can receive a superset by choosing a set of directions D, so just a set of vectors, and then computing the support function for each direction. And yeah, take these half spaces that correspond to the support function, and then take the intersection of all these half spaces. So this is always a superset, and if you actually use all directions that are possible, then you actually get equality. That's what I said at the very beginning, that half spaces can give you any convex set if you just use enough of them. But in general, you would need infinitely many of them, so that's really not practical. But you can get better and better approximations like this. So then we have a function overapproximate, which takes a set, and for some other arguments, for instance, a set of, or a vector of directions. So in this case, I use this Euclidean ball. And these 6 directions. And again, there's a plotting issue. Now, so these are the directions east. I should make it a bit zoom out again. East, northeast, northwest, west, southwest, southeast. So in 6, I evaluate the support function in 6 directions, and then take the intersection of these half spaces, and then I get this shape, which is clearly an outer approximation of the disk. And you can imagine that if I added more directions, I would get a better approximation. So if you don't pass any argument, we will interpret it as the box approximation, which you can usually compute efficiently for many sets. Then there's also some convenience wrappers for octagonal directions, for instance. In 2D, this gives you this, well, octagon shape. Of course, it depends on the actual set X. So in this case, it's a perfect octagon, but in general, it might look different, of course. What is maybe most interesting is that you can use this idea to approximate a set with arbitrary precision. So you can also pass a number here, and then we will compute an approximation that is epsilon close, where epsilon is a number, usually small. For those who know about this, close in the Hausdorff distance, but I will not explain this. Here's some large piece of code to explain what is going on here, but I will just show the plots. So let's say this is our original set. We always start with box approximation, and then we start, so you can think that we have these 4 directions here to compute the box approximation, and then we will, in the plane, so this only works in 2D, in the plane you can always say, let's take the directions that are between those that we have used last. So in this case, these 4 diagonal directions, and then just cut this part away. Then compute the gain that you have and compare to epsilon. And if it's still above epsilon, then you continue. So in this case, we have this this direction and this direction. So we take the direction in between again, cut away this part. Of course, we wouldn't do it in this order. We would first cut away the larger parts. But this we would just iterate until the error that we reduce is small enough, so smaller than this epsilon. So this is actually how we construct these plots, for instance, of these Euclidean balls. So whenever I plotted a Euclidean ball, it was not actually an exact disk, but it was just a polygon with lots and lots of vertices. So I can demonstrate this by reducing this resolution epsilon. So the default is 1 to the minus 3, and now if I use 1 to the minus 2, you can actually start seeing these vertices here. Yeah, then if you can do over-approximation, it's actually not so surprising that you can also do under-approximation. The idea is similar. You compute in this case the support vector, so the points on the border, on the boundary of the set, in some given set of directions. So for instance, let's say we have this disk again. Then if you approximate it with, let's say with octagon directions, then you get these 8 points. So you get these 8 directions, and then of course the support vector for these directions in this case is unique. So you really get these 8 points. And then you take the convex hull of these points, and that is your under approximation. This works because the set is convex. And yeah. And you can, of course, do this for box approximation. That gives you a coarser, so in this case, a smaller under approximation. And you can, in principle, play the same game and get an arbitrary close under approximation, but we don't have that implemented because we usually, in our applications, we usually work with over approximations, so we don't have the need for it, but it would not be too difficult to edit. All right, so this is basically the most important stuff that we wanted to convey. Now I will briefly mention some other things that didn't fit into this part yet. So we have, of course, some other operations on sets, for instance, something you often need, but it's not very exciting, is you can output the dimension of a set. Then you can do membership checks in most cases. You can check whether a set is empty. This is usually not difficult, but if you have lazy operations, it's not that easy anymore, and you need to really be careful with intersections. So for intersection emptiness, we actually have a convenience function that just receives 2 arguments and checks whether the intersection is empty. So yeah, here's an example. If you have this blue and this red set, then they are both 2-dimensional. Then we can have this small vector z, and it's not in the blue set, but it's in the red set. The intersection of blue and red is not empty, but the intersection of blue and this singleton is empty, of course, and the same is true for this one. Yeah,
let me add that we have all these different functions because sometimes it is easier, for example, to check if 2 sets are disjoint than to actually compute their intersection.
Yes. So usually we try to avoid computing the intersection for that. Yeah. Then there's sampling. This is also something very useful. I don't know why it doesn't work. Sorry, now I need... This is not the sets that I wanted to have here. So this is the blue and red set from above again. So here I sampled 100 random points in the blue set. These are the green points, and 30 points from the intersection. And this intersection is lazy, so it doesn't really compute the intersection. But sampling from a lazy intersection is easy. So what we use here in lazy sets is rejection sampling. So you just sample a random point from the box approximation, and then you check, is it contained in X and Y? And if so, you return it, and otherwise you sample again. Yeah, something I wanted to mention is that we have a rich type hierarchy in lazy sets. This is maybe a bit unusual for a Julia package, but this is because of the nature of these lazy operations. So if you have a lazy operation, you really don't know what is behind it, because anything can be behind a lazy operation. In particular, a deeply nested lazy operation again. So what we did here is create some interfaces. So for instance, the top interface is lazy set. So anything that inherits from lazy set is something that we can work with. Then there are some, for instance, a polyhedron. If something is a polyhedron, then we have certain assumptions about this set, and it also has to provide some basic functionality, like for instance, has to give you the constraints. And then based on that, we have many default implementations that just work. If you have a new set type that implements this interface, it will just get lots of functionality for free. Not necessarily optimized, of course. It's not unusual that if you exploit your additional structure of your set, then you can get lots and lots of speed out of it. But at least it will not crash, but give you some result. This is just a dash because in Julia you don't actually have multiple inheritance. Yeah, so here these are the subtypes of lazy set. If you go to the bottom of the tree, so these are all the concrete set types. Most of them we have seen. It's 26 in total, and then we have 18 lazy set representations, and I think we saw, except for this one, maybe. No, some of them we didn't see, but most of them we saw. And then there's, as I said, also these array versions. Yeah, so if you want to add a new set type for lazy sets, you need to implement dim to compute the dimension. This is usually very simple. And you need to compute the support function and the support vector. And then you get basic functionality. So for example, so this is a bit inconvenient and not really Julia-like. So if you have an external type, you really have to create that you don't have access to. You really need to create a new wrapper type, like we do in lazy sets. So our interval is just a wrapper around interval arithmetic.interval, but it's necessary with this design.
And let me mention here that there are other set representations not in that list that we have used, such as the set unions that were implemented in lazy sets, set union, and then you have a lazy rectification to work with neural networks with value activation functions, and then we have polynomial zonotopes, and also we can interface with cellular models, but all these other things are perhaps are a bit more advanced. We can comment on them.
Yes.
Later.
So as I said before, lazy sets is basically designed for convex sets. We are going there to also support non-convex sets, but for now, this type hierarchy only contains convex sets, and that allows us to make certain assumptions. And we're working on detecting these assumptions and actually getting around so that we can add non-convex sets to the family. But this will still take a bit, I think. So one of the last, I think it is actually the last topic I want to touch, is numerical tolerance. So all the lazy set types are parametric in the numeric type. So you can easily create, for instance, rational entries. So, and we try to preserve them in the operation. So if you take two squares with rational numbers and you call intersection, then you get a result that is again uses rational numbers, and not just by converting to float, doing the operation and converting back to rational, but really doing the operations exactly as far as possible. And yeah, something that might pop up if you use lazy sets in practice is that we have some internal tolerance, and if you have very small well, you need a very high precision, then it might be that you don't get what you expect. So here I have a function that just creates a V polygon with the vertex on 1 and almost 1, 1, but it's 1 plus 10 to the minus 9. And the default relative tolerance in lazy sets is this, so 1.5 times 10 to the minus 8. So this is smaller than this difference, right? So lazy sets will not be able to detect that these are actually two different vertices. So as I said before, the V polygon will actually do some pre-processing, so it will reorder the vertices and also try to remove those that are redundant. And in this case, it would actually remove one of these vertices because indeed they are redundant with this tolerance. But if you want higher precision, you can set the tolerance. This is not an exported function, so you need to do it like this. So if I set it to 10 to the minus 9, it will actually not remove that vertex, and you get what you expect then.
I would like to stress here that we work hard in order to ensure that all intermediate computations, when you do membership checks, disjointness checks, intersections, and so forth, they use this tolerance that you can fix when you work with this library. And this is a powerful concept. In fact, if you see in your line 11 in that cell, you will see that the function that you call to set the tolerance has two arguments, and the first argument is a numeric type. So in fact, you could use a new numeric type and then just set this tolerance, and then you compute. We had some time ago, we had someone opened an issue in lazy sets, and he wanted to differentiate, to use automatic differentiation through some of the lazy sets code. We never did this ourselves, but then when he had to change just a few lines of code, and then it was working. So I think this is also the power of Julia, that we are able to write lots of generic implementations, and then you have new types and you can compose, and the code still works.
Yeah, thanks. Right. I still wanted to say something about external packages. So of course, there's lots of functionality inside lazy sets, but some of the functionality also relies on external packages. And if you load them via requires, then you get this functionality for free, as you are probably used to. So I already mentioned Polyhedral and cddlib. And I also mentioned Optim for optimization, which is used for these lazy intersections mainly. Symbolics you can use for creating sets symbolically. I already showed that at the beginning. Then there's static arrays. Marcelo mentioned that if you use them, you can get another nice speed up usually. Distributions you can use for sampling in a non-uniform way from lazy sets. Maki to plot 3D meshes. And there are three others that are, I would say, very specific to applications. So you can compute the lazy exponential map. I think Marcelo might say something about this later, so don't worry if you don't know this. There's a package for the Delaunay triangulation, and we have some convenience functions to interface with that. And then recently we added some convenience functions to plot, to create smooth animations with Jarvis. Yeah, that brings me to the end. So I want to give some statistics. So we started this 4 years ago, this package, mainly Marcelo and myself. We now have, well, it was really a small project for a research project, just some library for defining some basic set types. But by now it has really grown a lot. We have over 100 source files with 20,000 lines of code, and lots of tests and documentation as well. And yeah, there were many other contributors, as Marcelo said at the beginning, even 2 or 3 even, Julia Sum of Code students. And we used lazy sets as the backend in many research work already. Yeah, so as you might have seen, there's really a lot of functionality in lazy sets, but that also means that many things are not optimized, because we cannot possibly optimize all possible combinations of these set types. We will never be there. But if you have a concrete task, feel free to open an issue, and we might be able to sneak out some nice speed up by just implementing a 3-line specific method for that. Yeah, so that's also what we do. So whenever we find that our results are not satisfying, we go to the basics and see that something is really using a slow default, and then we add this, and it really gives you sometimes orders of magnitude. Okay, so this is it from my side, from the lazy sets presentation. So I think there are no more questions, so we continue with Marcelo, I would say.
Well,
okay, then I'll switch to your stream.
Well, thank you for this great introduction to lazy sets. And at this point, I will present, this part on reachability analysis. So we will start. Giving some examples of what you can expect from this lecture, and then we will see the set propagation in action. So I'm assuming that you don't know about set propagation, about reachability, and we will try to build things together. We will see, first we will consider a problem in discrete time, and then we will consider how to incorporate models in which time goes continuously. And then we will see other a bit more sophisticated techniques that are used to study higher dimensional systems, to study systems which are non-deterministic, and then we will end up with some topics of current and future research that I hope you will like, you will enjoy, and then you will ask questions. You can find us on the Gitter channel as well. That we have a Gitter channel for communication of the JuliaReach team that you can find on GitHub. And we are also using Zulip. There is a channel called Reachability Analysis that you can also find us. So, okay. So then, okay, so if you load reachability analysis, you will see, well, that you can define a problem given by a differential equation, but where your initial state can be a set. So let me give you, I suppose, the simplest example I can think of. And it is a differential equation in which x dot represents, like in math, the derivative of x with respect to time equals to minus x. So, which has a solution that decays exponentially. And so I'm able to define, using this macro at IVP, a formula in which the set of initial states lives in this interval that goes from 1 to 2, and then I can solve it, specifying perhaps the final time. So saying that I want to simulate from time 0 to time 5, and then you will get some results that you can plot with the loading the plots library there, specifying the variables that you want to plot, like 0 being time and 1 being, in this case, the variable x, and then you can see this nice plot. At this point, you can identify that we have taken inspiration from other mainstream libraries in Julia, such as those in differential equations.jl, that let you interact with your models, with the solvers, with the plotting functions in a very nice and intuitive way. So let's consider for this example what we are showing here. So essentially, let's define a range of time values from 0 to 5, and then I can plot the solution together with the trajectories starting at the endpoints 1 and 2 and top. So you can see there are these two magenta lines that are converging to 0 as one would expect. And now, well, let me go into some of the details that explain what is being represented here. So first, we have the notion of Reach sets. So what is a Reach set? Is like a struct that holds a set and the time interval that is associated to it. So in this case, you have a set that goes from a little bit below 1, I will explain in a moment why, to 2, and then it spans some time, which in this case is plotted in orange. And then if I plot the 10th Reach set, it goes to 10. So the solution structures, this is what you have obtained from immediately after calling solve. So this is a structure that implements well, the Julia's array interface. So you can choose the solutions at different time intervals like this. Okay. So then the time span, when I say about time span, in this case, you will check with this function tspan that it goes from 0 to 0.05. And for instance, if you take the 10th reach set, you will check that it goes from 0.45 to 0.5 seconds. So why is that? Is because the algorithm that was used by default has a fixed step size of 0.05 that you can change by specifying the arguments when you call the solve function. Okay. Then let me also comment that what happens if you checked with the set, if you take the reachable set, the first reachable set that I showed above in red, then you will see that the interval that is spanned in the vertical axis goes from 0.948 to 2. So why does it go a bit below 1? Because this actually represents the solutions of the differential equation from time 0 to time 0.05. That you can check that the solution has gone a bit below 1 in this time span. So it's like saying that if I start over there, so the vars, when I specify the var arguments, is exactly the dimensions that you want to plot. Thanks. The vars argument in the plotting function. So when you say, if you look carefully at the first set here, then you will see that the solution that started at 1 and then it starts to evolve, starts to decrease exponentially, and then at time 0.05, it's a bit below 1. And so what we are doing when you plot these reach sets is to capture that change in the state variable. And that's why if you're going to plot the set wrapped by the first reach set, you will see that it goes a bit below 1, and it should cover it. So it's over there. Okay. In this notebook, I have some exercises for those of you who are interested to continue exploring this material. We prepared a lot of material, and we will stop in some places and give some comments. But in reality, you can spend much more time to actually work out all these examples that we have prepared for you. So then let me introduce an example in which we see for the first time what we mean when we say set propagation of a dynamical system. And then it is the following example. So the following problem. So suppose that I give you a matrix M that depends on a parameter theta. Some of you may be familiar with this matrix. It is called a rotation matrix, and it actually can be applied to vectors in 2 dimensions. And here I ask you to consider the set of points in the plane that span the box, whose x coordinates goes from 0.8 to 1.2, and then the same in the vertical axis. And then I ask you to compute the successors of that set subject to this matrix. So if you play a bit with this matrix in Julia, so well, essentially like that. Okay, so let's define the things here. So I have a Boolean infinity norm. So I have a Boolean infinity norm to encode the information on the problem, because I have, if you think about this, well, it's a square, so it's a Boolean infinity norm. The center at 1 in x coordinate, 1 in y coordinate, and then the width is 0.2. So we can implement as in line 2. And then in line 5, we can also implement in Julia the rotation matrix even above. And then you can plot things. For example, I can take the center of the I can take over there, I can take the center of the box and I apply the matrix and it will go there. And I can take the vertices of the initial box and they will go there. I can also take a few points in the first box and then apply the matrix to each of those points, as you see in linear algebra, and then it will just move the points around, and this is all good. But in a sense, this doesn't give the full picture of what's going on, because we are actually using points, or what we call singletons, like a set with one element, to represent the solution. And while that gives you the solution for time, you have to choose one specific point in order to apply it. So in our approach, we would like to have a more global way of describing the solution, and this is why we use like set types as provided by our libraries. I'll show an example. In this case, what is the question might be, what is the proper way of describing the solution to this problem? So if you recall the previous presentation, so we saw that there is a set representation called Zonotope, and so the Zonotope lets you represent sets that are the linear map of a hyperrectangle. And so it sounds more complicated than it actually is, because if I give you, for instance, the set, let me show you an example. So if I give you this set x0 that I call the volume with the center 1, 1 and radius 0.2, and then I want to operate with this to see like this, to see this object as a Zonotope where I apply things, the matrix over it, then well, I call lazy set convert function, and then it returns me this. Why does it return this? So this Zonotope contains two parts, right? So this is the center of the Zonotope, and then this is diagonal. If you plot this generator's matrix, you will see it is a diagonal matrix. So if you recall the mathematical definition of a Zonotope, so it's a linear combination of some vectors that are called generators. So that's why if you span all these different columns of this matrix with the combining factor, and then you add them up, then you will span the initial box. So this is a next representation of the same set, but using a Zonotope instead of Boolean. And this is all this interplay between different set representations that is interesting to us. So I recall here the definition set, but we are all on the same grounds. If you have a Zonotope, I was showing above the different columns of the matrix. So we have, if I have a box, I have a diagonal generators matrix, and so they are stacked representing these vectors I, and then you combine. And this is good. You would say, what happens if I take the matrix M to propagate that set? And then you see immediately that if I look at the second reach set that we obtained using the rule, this acts as applying the matrix M that I evaluate at 2 pi over 50, just to give a small step. And then I apply this matrix to the generators of the first set, and then I get the same object. So this is to show you how is lazy sets working in order to apply the sets to the previous one. So this is good. You can see that if I take the set and I represent the different successors using Zonotopes, well, I can describe all of them. And you can also use, well, fancy animations. Now, I mean, the reachability analysis library is a library that helps you to build all these objects, and where you can associate, for instance, time. Let me explain a bit about the time part that I didn't talk so far. So if I take a reach set defined, by our map, and then I can store the information of time. Well, in this case that we're considering so far, well, time is a discrete point. So then if you create this list, then you will, well, observe that by specifying, the variables, you get the plot. You can also plot in time. Just because we have stored the time information, you can do like 0, 1, and 0, 2, and you will see these kind of plots. Okay. This is so far, for example, what I'm showing here. What is this? So it is a projection onto the x-axis in blue and onto the y-axis in orange of this, right? So at this step, what we did here was, for each step, we project onto each of these coordinates, and then we plot the solution. So this is the resulting solution. Yeah. Okay, so let me introduce another concept to go a bit farther with these ideas, and this concept is called a flow pipe. So what is a flow pipe? Then it is a way to think about unions of reachable sets. Again, when I think of one of these in particular, I talk about reachable set because it's a set that you can reach given your discrete dynamical system that you define in our problem up to that point, right? So if you think about flow pipes, it's a way of modeling, a full union of reach sets in different ways. So you call this function, for instance, flow pipe, and then you can build it, and then you can also they behave like the set union of the reach sets. So all this infrastructure builds on top of lazy sets in order to help us work farther into the application. So you can check things like this also implementing the array interface lets you do a couple of different things. For example, you can slice the vector, plot 1/3 elements. You can also ask for the time span. In this case, if I was asking for the t-span of the first 5 reach sets, you will see, well, the sequence of the vector is applied. You can also use it to filter. So it has also the evaluation interface, meaning that you can take a flow pipe, and then you can say, I want to look only at time t equals 2 pi, and then it will retrieve your result set. You can also use it to filter for an interval. So this is an interval from 2.5 to 3. And it reaches the view over the 4. It found that there are 4 reach sets whose time is between 2.5 and 3. This is what this means. Okay, and then you can also, for instance, to show you an example. In this case, I took the flow by f, and I pick only those reachable sets whose time span goes between time 4 and the final time of the flow pipe with t end, and this is a result that you will obtain. As we will see, all this functionality becomes more interesting when time is dense. We will see this in a moment. But for now, this might resemble what you get from an equation that iteratively gives you answer for discrete time steps. Okay. And finally, well, let me tell you that you can also operate with flow pipes as you would do with sets. So here I just take, the flow pipe f. I take a half space defined by x plus y smaller or equal than 1 over there, and I intersect them. Why? Well, because there are applications such as in hybrid systems where your system has a discrete transition. So you may be solving a problem, and at some point you want to take a transition to another mode of the problem, and you need to operate. You need to take different set operations, and then all these things are quality of life improvements, I would say, that are very, very nice to work with if you're using Julia. So this is the result in the case that you take the intersection between both. two things. Okay. So far, we have discussed, I would say, a motivational problem in which we were given a system which evolves at discrete times. But in practice, there are numerous applications in which the models that where we want to work are described by time, where time is a continuous variable, and this is the case for ordinary differential equations. So here I also choose, to bring an example that it's just one step, the most simple case that I can think about a differential equation with two variables might be the following one, and it is in fact the continuous version of the previous case. So this is called the harmonic oscillator, and you can check by hand that the solutions of these equations, when again x dot represents a derivative in time, the rate of change of variable x is equals to y, and the rate of change of variable y is minus x. So these equations are coupled. And when one increases, the other decreases, and then you will see these dynamics over the plane. And I'm also interested in the same set and what happens to this set when you try to apply this set to these continuous differential equations. Again, I was saying that you can check by hand that the solutions are linear combinations of sine and cosine functions, which depend on the point where you start. Okay. So, well, you can just write some code in order to write the analytic solution. I will go on and tell you a bit about the plots here, because it's something you can also play with and ask later if you have questions, specific questions about our examples. I think it's interesting to reason about the first and the second sets. So suppose that I take our initial box x0, and then I want to see what happens, a small step size ahead. So in this case, I am taking 2 pi over 20. At time 2 pi over 20, I take a picture. I take a photo of this, and I get the set in orange. The set in orange is obtained when you take your matrix and apply it to the set in blue. And so, but then you would say what happens between these times, because we have a dynamic evolution, we have a continuous evolution. So then you will see that if you pick any of these points and you apply the solutions of your differential equation will move describing circular trajectories. So they will, of course, escape the union of the blue and the yellow set for all those times starting there, because you don't have any set to represent what is happening between these times. So it's natural to ask, if I work with sets, may I represent what has actually happened between time 0 and time 2 pi over 20? So this leads us to our next topic, that is called conservative time discretization. So as I said, you could be interested in finding what happens between these two time steps, and then the first attempt might be to take, the convex hull. Remember, this convex hull was the minimum convex set that contains the set in blue and the set in orange. So this is plot with lazy sets here. You just have to do CH of x0, 5, and x0, and that's it. And then, well, it gets close, but then in fact it is like a linear combination of the different points, right? So for example, let's consider a zoom into what is happening here close to the borders. So in reality, there are all these trajectories that are close to this corner, which actually escape due to the system's dynamics. And here we took a very simple case, but it is general enough for illustration of what goes on in general. So if I take some random vertices over there, then at some point they will escape the convex hull. So while this might be an approximation, it is not good for our purpose. So then, well, there are some math results. I'm going to introduce some of them that actually tell you how to build a set enclosure of what happens over there. And if you think about it for a moment, From the mathematical side, what you have to do is in some way understand how does the dynamics escape from this, like this distance from the linear approximation to the maximum that it can go there. And well, then you get into some interesting math, and I will show you one of the examples first. It is not the most accurate ones, but I think it's simple enough to introduce first. So let me read this proposition. So essentially, you're given a linear dynamical system like x dot equal a times x, and the set of initial states there, call that equal x0. And then what this result tells me is that, if you build, what this result tells me is that you're not that far from the convex Hull approximation if you bloat the set a bit. Okay, how much? Well, this is told by this Minkowski sum here. So you have a ball of radius r, which you have to compute, and you can get some intuition if you look at these r. What are the parameters on which these are? And so again, this br is just a ball center at the origin and with a given radius that you can compute. You will do something like the exponential of you will take the step size, and then you will take the norm of the matrix A, and you take this operation, and then you will multiply by the radius of the set x, or the norm of the set x. So that's it. It tells, I mean, this first result, let's play a bit with it. Well, okay, there's a most technical comment that these conversions to the reachable states. I mean, we'll not enter into details today. So I'll enter into the intuition behind these formulas. So, if we get there, this is our exercise. Implement the above method. So, given that there are so many interesting things that we are going to present, I'll go quickly and explain the code and let you play with it and ask back if you have questions. So, I think it's quite interesting to note that while this might seem complicated at first, we have the lazy sets library, which in 2, 3, 4, 5 lines of code you have written your implementation. And well, of course, the key part is line 6, in which you are doing a lazy set operation, and all this is implemented already. Okay.
Marcelo, your connection is not very stable. I'm not sure. Maybe you could deactivate the video. I don't know if this is a good idea, but
yeah, sure. Okay, Ferdinand. Yeah. Oh, hold on a second. Yeah. Voy a conectar. Hi, I'm back.
Okay, yeah. For now it works. I don't know.
Thanks.
So now you need to share the screen again.
Yep.
Okay.
So
great.
Okay, so I was here. I was commenting that. Yeah, I mean, this is a nice exercise. If you check how to implement many of the things, and sometimes one is surprised at all the things. If it's not written in our package, there are so many other interesting Julia packages that implement many other things that makes it easy to prototype complex mathematical formulas. So in this case, well, we get some result. So let's check how good this result is in this case, right? So it's given here. So of course this is. Let me show you the plot first. Wait. Yeah. Wait, I had to run some notebooks from above. Hold on a second. Here. So it's there. Yeah. And now I will plot the result. I think the connection improved. Thanks. Yeah. So that's our first result. If you check at the what is being plotted here, so I have 4 sets. Remember, we have x0, then we have phi times x0, where phi is a matrix is our matrix M. I called M and because phi is a matrix exponential of the dynamical system. So it's simply as that. This matrix phi is a matrix M from the discrete problem that tells you how do you propagate in space. Okay, and then from time 0 to time 0 point, from time 2 pi over 20, or what is the step size here, then you go from the blue set to the orange set. And then we were saying, okay, so how can I know where these trajectories go between these time intervals? And then we saw that there is a mathematical result that gives you an approximation, and this is the set omega 0. Then I mean how to run some notebooks, like some slides again. Okay. Hold on a second. What's correct? So we were here, I think we were here in the discretized function, okay? We saw, the result. We saw that, well, it is fast. Of course, it is fast because it is only computing the set lazily, okay? And then we could ask, well, can we do better than this? There are other methods. There is this other method that I will not get into the details, but I let you for further exploration if you are interested. And these other results, well, essentially, it is a more sophisticated operation. Instead of just taking, the linear approximation, it will intersect forward, one step forward, one step backward, and then doing the second order approximation. You can experiment with it later with other systems. But I think the key part, if there is something that I want to remark here, is that while these different formulas introduce many operations, well, the implementation with the lazy sets library is really easy. If you check about the work that we require here, it's essentially taking again, it's 6-7 lines of code. So I think this is quite remarkable for a prototype that works. Okay. Yeah, this formula contains another operation that I think we didn't present in the last part. It is called symmetric interval hull. So what it does is essentially a set that includes the given. So for example, I have an ellipsoid E and the symmetric interval hull. It is the smallest centrally symmetric set that contains X, and it is centered at the origin. So, with operations like that, you can express the tighter result, and then we can also plot. I defined them. I defined it. Wait, I will fix it. Sorry. Yeah. Okay. So finally, the comparison between these two results, you have LGG's result from 2019 and another improved method that is plotted in red over there. So you can see that we get tighter approximation by using a more sophisticated method. And there is also something I was trying, a silly idea here, that in reality, that you get an idea of the power of this lazy sets approach, is that in this cell I have defined my JuliaCon set. It's something that it just holds a dimension, and then if you implement, the lazy sets interface, which at the minimum is just these two functions, line 5 and line 6, then you can already apply your discretization. And if you want, what's going on here is that omega is very improved. Let's call this different because it's JuliaCon. Okay. So why does it already work if I only have to define, the support vector? So remember, the main idea here is that you define rules in which the rules apply to sets that you define. Okay, so all what lazy sets is doing is propagating the information of those rules. So in this case, I construct take this new set representation, and then if I give you a vector, it also returns 1. In general, you could do other things for your set. So of course, this already works because what all that we have done in this function is to encode, this mathematical result without any a priori assumption on the set itself, right? I think this is a key part. Okay, so now let's continue with our examples in the following part. Okay, so now if you say, okay, now I have my initial set and then I want to see how it propagates in time, then you would normally apply again your matrix M, and then it will, as you can see, it is rotating around the origin, and it is containing all the initial trajectories for all the sets. So we have finished our first example of propagation of a set in dense time. If I have to summarize, so it's essentially, we will give you some algorithms that you can check later, but I think it's important to go farther a bit more. At some point, you can ask for help if you try this. So, as a final result, let me tell you that again, this theory that we are applying converges from outside to the trajectories. And what this actually means is, in this example, I am using I am using a smaller step size here, and I'm propagating forward in time this set, and then I get also solutions that I can project in time. And someone says, amazing work, this is very valuable as long as it is scalable. Well, yes, I can advance that it is scalable for linear differential equations. And we also have experiments with higher dimensional linear differential equations, which are hybrid and which have non-determinism, and that is much more complicated. We will not enter into all these details because it will take us too far, and we also want to talk about nonlinear reachability, a domain in which it is not scalable yet, not because we don't know how to do it, but it is not known. In general, it's an open research directions, and there are amazing work done by different groups about these topics, but we can still do very interesting things there. So yeah,
maybe we can still say that it works for hundreds and thousands of dimensions for linear systems.
Yes. Thanks, Christian. Yes, I'm going to present some results. So let's say I'm going to present, some results and then some ideas about how to work with high-dimensional systems, and then I will go to other cases. So, at this point, some of you may ask, again, why do you study linear systems if the solution is known analytically? Well, the thing is a bit more complicated than that. In fact, yes, you have analytic solutions when you have a situation in which you can control the initial state and in which you can control the input set. That's correct. But there are many cases in which you don't control this because your model describes physical systems, whatever, engineering systems, biological systems, economic systems in which you have uncertainty. So at those points in which the problem is more complex because you have initial non-determinism in the sets and also in the input sets. So it is there where these methods give interesting results, and I want to give you some very simple problem, but I want to fix some ideas. So suppose that I tell you, well, consider this safety verification problem, okay? I give you a set that I call the bad states, and I want you to decide whether or not the system is safe. So what do I mean by the system, if it's safe or it is not safe? Well, I want to check whether there are no trajectories or behaviors which enter into the unsafe or bad states zone. Okay, this is called safety verification problem. And I want to check this not for one initial condition, not for 100 initial conditions, or for 1 or 100 input functions, but for a whole dense set of initial conditions and dense set of input functions.
Marcelo, there's a follow-up question in the chat.
Someone asked if it is possible to use it directly on nonlinear systems, and this is yes. I mean, there are several approaches for. I can understand that people are interested about nonlinear reachability. It is an exciting topic that I will present in the next hour. Yes, there are approaches in which, if you want to keep the property of formal verification reachability with the system that has been linearized, because you have a nonlinear system, then you linearize, then you have to ensure that your linearization is conservative. So this is a possible approach, yes. I will not present it today, but it is a nice idea. It exists, this approach. Okay? So yeah, just to summarize this simple exercise. So I have taken again the simple harmonic oscillator. I have taken an input set capital U, and I given you that that the input set U lives in the interval -0.1 0.1. Yeah, I didn't enter into all the mathematical details of how to actually compute with bounded but arbitrarily varying functions. It would take us a bit too far again, but the idea is the following, okay? While when you are propagating sets, you can use them to bound integrals. So if I have the part, when you write down this solution and then you have an integral on the inputs, you can use that information to bound the possible results of your state. And that's how it works. And that's how this result that I am showing here is the solution for all possible input functions which are bounded between -0.1 and 0.1, but in time they can vary arbitrarily. So this is a very general result that you cannot simply simulate. Even in this two-dimensional case, you cannot simply simulate using random sampling of this U. Okay, and so you could say, okay, I can take my solution, call it sol, and then I can ask questions whether is it between time 0 and time 30? What is the maximum value? So you take the flow pipe, you take a direction, in this case, the direction positive x, direction negative x, you apply the support function and it gives you a result. And so what does it result represent? So what it tells you, again, is that the maximum value of your state variable x between time 0 and time 30 has not exceeded 3.49. Okay, so you can see in the plot here. So you can start to see the connection between support functions and verification of, in this case. Okay. I would like to spend a few more minutes into a high-level introduction to doing reachability in higher dimensional systems. Okay, so first, let me say that, well, for those of you who are asking about the scalability of linear reachability, yeah, it's well, here are some examples. So suppose I take a set H in dimension 1000 and a matrix A, and I make a very simple operation, so just taking the linear map. Well, this is compiling. So in fact, it's faster than much time. I mean, I think in general, what you can expect is that you can operate with sets of thousands of dimensions, and if you are working with more than 4,000 dimensions, then we have been used successfully methods that are called Krylov subspace methods to propagate with the matrix exponential. I will not enter into that detail, but that's it. That's the main idea. And now let's focus a bit on what's going on here. So I start with a high dimensional set. Okay, fine. So can you actually represent? Can you actually what things you can observe? Yes, you can do many things if you combine this. If you combine what we saw in the talk about lazy sets, because in fact, if I can take this high dimensional set and it has some like 2 to the power, 1000. I mean, an incredibly large number of vertices, but you can still find useful information in very little time. I think this is a bit surprising, but it is because the mathematics allows you to compute the support function along the projection on some of the combination of variables of your choice, and then you can make visualizations like this. So that's the idea. And of course, evaluating support functions in 2D is much cheaper than computing in the full dimensions. So, so now I would like to go more towards the actual results. Okay, so the idea is the following. So, yeah, remember that we have, I will explain this picture in a moment. So remember that we have like a way to propagate different sets using some objects that are zonotopes, in fact. Okay, that is fine, but sometimes it is not general enough. So sometimes if you look carefully at our result when we were doing this conservative time discretization, if you remember, and if you look carefully at the result that we obtained, then you will see immediately, where is this plot? Is here. So you will see, for example, the plot in orange or in red that I called omega 0 here. Well, this set is not a sonotope. It's not a sonotope because it does not have pairs of parallel sides as sonotopes should have. So then, I mean, in reality, when you're going to propagate this set, then you're gonna just say, yes, I take a sonotope of this. You have to approximate it in some way. So this is something that you can do. But then you can also take the lazy representation of the result and then propagate it exactly using support functions. I think this is an important concept. So again, I take the set omega 0 in its lazy expression, and instead of approximating with a sonotope or with another simple set representation, such as a hyperrectangle or something else, and to apply the dynamics on that simplified object, I don't need to do that. In fact, I can take the symbolic set, omega 0, and then I can apply, for example, support function evaluations to propagate the set without further approximation. So this is the idea, and this is the reason why, if you look at these plots here, why if you look at those plots which I was showing over there, you will see that in fact they are tighter than the box approximation for the first and second reach sets, right? So I don't know if you get the idea, but you can see here, if you look a bit even more closer, then they are not exactly touching it, the edges, and this is because if you remember when we presented the support function of intersections, then there is a smaller or equal involved there, and then we still get, even if we don't get the exact omega 0 in this particular case, we still get a very good approximation. Think that if the set was completely tilted, then this evaluation in some direction would give you a very good approximation, while using the axis aligned box will not. Okay. And now I have prepared another example to show you a bit of the to show you, well, that you can use your own what we call template reachable sets. So what is a template reachable set? Well, you specify a set of directions in which you want to propagate your set, and then this is used in all the computation. Okay, so here in this artificial example, I took the Julia logo balls, and then I made them to live in a 5-dimensional space, and then I define a continuous dynamical system that is acting on the 5-dimensional space, and then I compute the flow pipe by projecting on 2D. Okay. So to do it is simpler than all this what I said, because we have interfaces to define custom sets of directions, and in that case, what the result that you would obtain is like this. And I think again the important part to in time and in space, I think the key part to consider is that you are able to define your approximation. In this case, your support directions will, for example, you can take them to be to live in the 2D plane, and then they are free on the other dimensions. Okay, so these are some results. And now to go further, my final topics is to give a few more examples of reachability and how does it compare to perhaps to more traditional simulation-based approaches. I have prepared a few examples now, and well, we have this helicopter model used in some articles, where this is an 8-dimensional helicopter model with a 20-dimensional controller. There is like a control plant that is it's a problem from a book about control, and then in fact you couldn't possibly study all the millions of corner cases, so we have considered solving this using JuliaReach. So here I am showing all the steps. All the steps that are required. In fact, you start by defining a model. In this case, we have a model library called Reachability Models that we are developing. And then you would load the model and have your initial value problem and then solve it. In this case, you can see in algorithm 1, in line 1, that we specify a few of the options that are required for the solver. And the options that are required, essentially the key part is this and this. So after defining your step size, you define the variables that you want to compute and the dimension. And I have to stress again that what this means is using this technique of observing the evolution in only some directions, this scales very well. I mean, this is a small example, but I think it's a nice one that we have used in other cases. It takes, of course, this is after, this again includes the compile time. But in general, what you can expect is, I mean, here we have computed the variable along variable 5 using support directions in that much time, so less than 1 second, and you can compute also all state variables if you want. And also this is simpler to do in parallel because all these directions are independent, so this takes that much time to compute along all directions in this case. And this is a small step size, so we have computed a few thousand reachable sets. So if you want to compare with what might be simulations, so I have some plots here. I consider two cases. In fact, I considered a case in which the inputs are constant, and in another case in which the input to this model is varying. The input in this model represents the external force of the wind on the helicopter. And here I have plotted a few variables to see the variable x5 that determines the yaw rate. And well, what's interesting here is again that the support function idea lets you analyze this solution when I can evaluate along this direction and I obtain a result that this variable does not exceed 0.11. So like this, you can do many other experiments. You can also plot the trajectories, comparing, you know, a few hundreds or thousands of trajectories and one flowback computation. Okay, we could go on, but I will prefer to conclude this initial presentation of linear reachability with a few more examples. Okay. Unless you want to add something, Christian?
No, it's fine.
Okay, good. Yeah. So, okay. And let's see. Okay, so about hybrid systems, well, I mean, these are other topics that we have considered, such as hybrid systems. Well, we also have an interface to define and to solve systems that can change discrete event because of discrete events. This is the hello world of hybrid systems. It is a bouncing ball, and well, I have shared with you the code that you can inspect in order to define the system. It's quite easy. It's quite simple. So you have a few. Let me just quickly mention the nomenclature just in this domain. So you have one or more locations. In this case, you just have one location that represents that the ball is falling. And then you have a flow of dynamical systems. You have an invariant that the invariant specifies that your system should, I mean, it should satisfy this constraint whenever it lives in this particular location. The hybrid systems is a very general formalism. You can model many other things, but you know, if you take this bouncing ball, you have defined a guard and a reset map in this way. And so we will encode all this information. What the guard represents, well, that the ball has hit the ground. So if you take the ball and then it will go up to the ground at 2x equals 0 when the velocity is negative, so it's falling, and then it will jump again, losing some energy. So this is what this reset map is representing. Okay. No, and then I come to this question that when we propagate dynamics of hybrid systems, how do you actually do this? Yeah, I will not enter into all these details that are very exciting, but it will take us more time. But what I can tell you from start is that we only use set-based operations. And we try to exploit as much as we can the information on the contained in these reachable sets. And it is also interesting that these methods do not require root finding functions, because they could miss champs, and they are not what is natural in this. What is natural to do here, I have this code that you can check later. So what is natural here is to use the intersections of the flow pipe with the other description of the model. So if you look carefully here, so all these guard, reset map, they're all sets. You can think of all of these are sets in the Euclidean space. So what we will do is to have a set that is propagated through this location, and then when it hits, for example, the ground, well, we have to take the intersection, with the ground, and like this you can build many other complex problems by propagating sets, taking intersections, and so on. So this is just to tell you that, and in fact, this is the interesting aspect of this model, is that it converges to what is called a fixed point. It means that the evolution of the hybrid system is such that at some point the algorithm detects that it has already computed the sets from a previous iteration in time. So what this means is you start here with a distributed initial condition, and then you start to bounce, and at some point I was asking the algorithm to give me the solution until time 30, but in reality it gave me until 12.3. And why does it happen? It's because you have found a fixed point of the method. So at this point, this is actually converging to the specified tolerance. Okay, so yeah, oh, sorry, this is also another plot that you might want to see. So if I start there, if I start here in x of t, then I start to bounce around until I get there. So that's all for this first part. You can check more at the notebook, and I will now describe. We have studied other more complex systems, such as filtered systems for filtered oscillators from electronics, from other case studies. Let's go directly to them. We have, and finally, we have studied. We are beginning to apply these methods to systems that are found in structural dynamics problems using finite element methods, together with Jorge Perez, and he will present a talk about this week at the mini symposium. Okay, so what comes next? Okay. Well, let's discuss a bit about nonlinear reachability with you. I don't know if you have some questions so far. Something else that, Christian, that you want to add or comment?
No, it's good.
Okay, thanks. So we will have, for the rest of this workshop, that we have half an hour left.
Correct.
Perfect. Okay, so we will present some results about set propagation for nonlinear systems, and then we will finally present results about propagation of sets which are controlled, or systems which are controlled by neural networks. All of these, many of these things, or most of the things, are ongoing research projects. At this point, I would like to comment that the work on nonlinear reachability is led by Luis Bennett. So thank you, Luis, for all this amazing work, and also to David Sanders. Let me give you a motivating example, and then a few other things that you could find useful in this domain. So here I took a simple 1D example, which is the solution of the differential equation x dot equals minus x times sine of t, okay, which is x0 exponential of cos t minus 1. So our first observation here is that standard integration schemes will fail to produce a solution if you pass them an initial interval which is big, in the sense that it is not just, you know, an interval of the size of floating point tolerances, but be like as in -1 to 1. So what does it? I mean, Julia is a great language, and then you all these this just works if this just produces answers. This is amazing. So you can use differential equations and pass this initial interval, and then, you know, specify, you know, your favorite solver, and then the result is going to be a sequence of intervals that grows and just grows. And why is it the case? Well, because these methods are not specialized to operate with interval arithmetic, and then the dependency problems kicks in. So when you take powers of intervals, and then if you have formulas which involve intervals, and you do this in a naive way, then the evaluation of that formulas just increase. So there are solutions, but then these solutions require that we spend some time analyzing other strategies. And in this part of the presentation, I will give you a few hints of what's going on in this Taylor model-based solvers. And this is the same implementation as what you had above, that such that it can be interpreted and run in JuliaReach, more specifically in our library reachability analysis. So the main change is just perhaps line 15, where you specify another solver. In this case, it is called a solver called Taylor model TM-JETS for Taylor model, and JETS, this is a technique that is available in the package Taylor integration.jl, led by Jorge Perez, but another Jorge Perez. So essentially, we found a solution of that result that is propagated using Taylor models, and if I plot on top of this solution the trajectories, well, they match very well. Okay. In fact, the Taylor models are such that they track the initial interval when it shrinks, and it enlarges again like that, and without accumulation of error, what is called the wrapping effect. So this is a way to illustrate the results. And let me now perhaps give you a very high level idea of how these things are represented. And these are represented in something that we call Taylor model Reach sets, and Taylor model Reach sets are essentially expansions in space-time. Why they are expansions in space-time? Because they involve the time variable and a time span where this Reach set is valid, and an expansion also in space. In the space, meaning the variables that describe your ODs. So in this simple case, you can identify that there is that if I check the first reachable set, then this is an expansion in time. This is in fact called a Taylor model, which is a polynomial together with an interval range, and the coefficients of these expansions in time are themselves expansions in the variables. It's a fantastic and very expressive way of representing solutions. And then have in mind again that this is not just one polynomial expansion for the whole possibly large time horizon, but this is a union of all these different reachable sets for different time spans along your T. So this is the result that you obtain. And then I want to present. I'm not entering into technical details, which are exciting, but we have other things to present today. So what I can tell you is that if you exactly this is the Taylor models representation that I was commenting earlier. So in fact, you also have conversions. You also have conversions to the true reachable sets of the nonlinear ODEs by changing the parameters of your expansion, right? So, and my last example in this part of the presentation is going to be the Lotka-Volterra model, and to tell you how do you code this and what are the possibilities of the of these techniques. Okay. So perhaps all of you are familiar with systems which are parametric in some coefficients. For instance, alpha. In this case, it has 4 parameters to describe the dynamics of population growth in systems. So you can implement it like this. So you may be familiar, for those of you, again, who are familiar with the differential equations suite, we have this matches that definition, so you can use your models. And essentially in the cell below is where we specify that our solver should be a Taylor model jet solver, and then we plot and then we observe this plot. Okay, so what happens here is that we were able to propagate the full box of initial conditions through this differential equation, and then usually this is just the beginning of the analysis. Why? Because first, because of the plot. What this plot represents is in fact an over approximation of all the information that is stored in these Taylor models. If you think about it for a moment, when we say that the reach set represent expansions in time and in space, then you could say, okay, but then if I want to plot, what is actually being plotted is the evaluation of the range, and then you have to decide how do you evaluate this range. And we are building tools that let you evaluate this range in precise and efficient ways. There is always this trade-off that you can always over approximate using interval arithmetic, perhaps using just one evaluation and get very quick results. But then if you want to operate, perhaps you have to do more detailed techniques. I have some of them to explore, that you can explore in this notebook, that you can ask questions if you start to work with this, or you want to experiment further with this. And you will find out that, yeah, there are many things that you can do. This is very flexible, and one of my last examples in this part is going to be some test that I did, and I prepared it for the workshop. And it is what happens if can I propagate, like my question was, can we propagate the sets which are non-convex starting from the initial set which is non-convex? Can I propagate it through the differential equation? So as it turns out, I could write an example in which my set of initial states, instead of being a box, it is a parabola. So in principle, you can take this non-convex set, this parabola, that again is described exactly using the Taylor model reach set representation, and then you say, let's encode this into something that you can feed the algorithm, and then you can propagate it using the method. And for the method, it's the same if you have a box or another set that is parameterized in this non-convex way. So I was surprised to see that all of this actually works. If you see the results, again, these results are less precise than what is actually contained in the information, but you can already, but that's because visualization. And then you can see that if you start with a parabola here, it will propagate like that, and this is the main idea, right? So you can also continue like that. And again, this is one evaluation in which I didn't have to sample the parabola. I simply describe the parabola in a way that is friendly to the Taylor models method, and then it will automatically use the solver to propagate it through the system. So that's the idea. And then to conclude this part, I have another example of this. To give you more ideas on the possibilities of these approaches. In many cases, you have systems which are in which the parameters are not known with certainty. So in those cases, one possibility is to add those parameters to the dynamical system. In the simple case here, I just take the parameters alpha, beta, gamma, and delta, and I write them as being coefficients in my dynamical systems, and then I put, for example, that the evolution in time is 0. So they are constant, but I can specify that they are interval valued. I mean, that's the idea, right? So I would like to propagate a set in which the initial parameters live in some domain, for instance, in a box. I could take something else. In this case, a box. If you look at line 3 carefully, you will see that we have a Minkowski sum of nominal values of the parameters plus a ball in the infinity norm where I can specify the widths. So what I'm doing here is to say, let's decouple the system dynamics with the parameter variables, and then let's take this is all using lazy sets to work with Cartesian products in the higher dimensional space. This is in 2D. This is in the dimensions of variables x and y, and then this other part contemplates the uncertainties in the parameters. And then you can send this initial set to the solver, and then what you get is a set that has been bloated because the set in blue. The labels are inverted. Sorry, nominal parameters are bigger. The distributed parameters are bigger because they have more behaviors that are being described in this solution, right? So they have all these behaviors for all these possible values of the parameters, and then of course, and again the situation is that you end up with a solution that is a polynomial expansion in the different variables. If you check, for example, if you check the polynomial that is obtained that is represented at the parameter alpha, then as we specified, it is constant. So this is a representation that it spans the initial interval that I gave it to it. And then if I look at the expansion for the first variable in time, then it will appear. So x4 is a parameter alpha that appears here. So you can evaluate in many different ways. I didn't enter into those details today, but there is many possibilities in which you can extract the information of what is the effect on parameters that are distributed on the solutions. Okay. Well, I leave you other examples for further exploration, such as that you can find in the documentation of reachability analysis. If you try this, again, send us your examples. We will include them in the documentation of our packages. So get in touch. This is an example of invariant set computation for the oscillators, because using these methods, you can check whether a system that oscillates enters into the behaviors that were from where you start, and then you can find this way you can algorithmically prove invariance and other interesting properties. We have also used this method for verification of more complex nonlinear differential equations, such as the equations describing this quadrotor. And here are some results. Every year we have been participating with other members of the reachability community in order to improve our methods and to compare with state of the art, and then and also to have fun. And then you can find this on the internet, on GitHub. And I think that's all. My last model is going to just quickly mention that another example application of these techniques is in nonlinear hybrid systems. So before I mentioned about hybrid systems, and then again, hybrid systems arise naturally in these models in which you have nonlinear dynamics described by switched controllers. In this case, we have considered that an interesting aspect is that we consider non-determinism in the switching times. What this actually means is that using set propagation, you can assume in your model that the transition to other mode can take place at any time between 120 and 150 minutes. So the transition can take place at any time, and you can propagate the possible solutions in this time interval. And getting a global description of all these possible behaviors. And that's my last result for this part. We still have Say with us, because we now are going to present these results on neural network. Christian, you will present this whenever you want.
Mm-hmm. Yeah, thanks, Marcelo.
Thank you. Thank you.
This is also a great theme, because we will continue with hybrid systems, control systems. In this case, the controller is implemented by a neural network. So this is implemented in the package neural network analysis. It's not even released, so if you want to try it out, you need to check out the code from our repository. So to just give a very brief introduction, you have a planned model, which is an ODE system, and you have a neural network controller. And in this notebook, we consider periodic controllers. So every multiple of some period, let's say every second, the controller samples the current state of the system and then takes that as input, and possibly some external input as well. The neural network gives you some output, and then this output is used as input to the planned model again, and this is then called a control input. And this is really used in lots of areas in science and technology. And yeah, these neural networks, of course, are on the rise, and probably this is already too old to say. They are already there. So what we now want to do is basically what Marcelo did before for these ODE systems, in addition with these neural network controllers. So we want to do this. Of course, you can again do simulations. So you can simulate an ODE. You can simulating a neural network is really easy. You just plug in the input and you get an output. That's exactly how it is defined. And then you can, of course, simulate this loop in the same way. But it has the same problems as before. You will not see the corner cases. You will not see all possible behaviors, but just one. Of course, you can do hundreds of simulations, but this is also expensive. And we will try to do this again with sets, so that you just do one propagation of sets through this loop. And yeah, in principle, this is the idea that we will use. Actually, we sample the set that we compute at a certain point in time. Then we somehow propagate the set through the neural network, get a set out, and use this set as input to the ODE system again. So in principle, we have seen most of this loop already. The only thing we haven't seen is this propagation through a neural network. But I will not go into this, because this is something that many researchers have tried to do, and they are better and more precise and more expensive solutions. In general, it's very difficult to propagate a set precisely through a neural network because of the nonlinearities in there. But I will not go into that. So what are the main features of this package? Well, you can do simulation, but you can also do set propagation. Usually we are interested in sound waves, but you can also do approximate waves that don't give any guarantees. What do we support? Well, nonlinear ODEs, because, well, we already have that in reachability analysis, and feed-forward neural networks at the moment with ReLU activation functions, but this is fairly easy to extend, I would say. So the main packages that this package builds on is reachability analysis for this propagation through the ODE. And there's a package developed in Stanford called neural verification, which implements some algorithms to propagate through the neural network from the literature. And we used one particular algorithm from there. Yeah, there was also a competition like the one that Marcellus showed before, also for these neural network control systems. And we also participated this year, and that's exactly why we wrote this package. So it's really brand new. And I will just, I don't want to go into the details, and there's also no time for that. I will just give an example what you can do with this package. And for that, I will consider one of these benchmark models from that competition. Here we have a unicycle model. So you have one wheel, which is described by x and y coordinates, a velocity, and the steering angle of the wheel. So it's a very simple model, of course. And then you have the control inputs, namely you can control the angle and the velocity. Or not you, but the controller, so the neural network will do that. We also assume that there's some external disturbance W, and in the following we will assume that, as Marcelo said before, we have this assumption that we don't know the exact initial value of W, but then after that, in this model, it stays constant. So this is the ODE for this simple model. We can write this down as before. I will skip this. Then we can load the neural network. So in this case, it's a MAT file which stores the weights and the bias terms and the activation functions of the neural network. So we just load this, and now we have this controller. Then this particular model has some normalization that you need to apply. So the output of the neural network needs to be post-processed by subtracting 20 from the two outputs of the neural network. So we can do this with the package by adding this uniform additive post-processing thing, which subtracts 20 from everything. The control period is 0.2. Then we can define the initial set. In this case, it's just a box. And here the last entry is this disturbance W. So W lives in the range from minus 10 to the minus 4 to plus 10 to the minus 4. Then we have the initial value problem. You have seen this quite a lot today. This U is just for technical reasons that we get a full dimensional set, but we will actually ignore it, so it doesn't matter what you pass here. It's maybe a bit inconvenient, but we can improve this in the future. Then you only need to define which dimensions are the state variables, the input variables, and the control variables. And then you put this all together in this controlled planned object. And this is then our problem that we want to work with. So far we have defined the model, and now we want to solve it. But no, first I want to define the specification, what we want to prove. So in this case, we say that starting from this initial set, we want to reach some target set, which is defined by this box here, at time point 10. So we want that all possible trajectories reach this box. And how can you do this with sets where we want to prove that at time t, the reach set that we compute is fully contained. And this is, of course, only a sufficient condition, but if we can prove this, then we have proved that really all infinitely many trajectories reach this set at time t. All right, so first let's start with some simulation. So here we can simulate this system. Here just say one single trajectory. Then I plot the initial set, it's this small box here. The target set is this larger box here. And now I add the simulation. So you can see it has some relatively complex behavior in this x1, x2 projection. Here I zoomed in on the initial set and on the target set. So you can see the trajectory really emerges from some random point in here, and it reaches at the end. So the simulation time is exactly 10 time units, so until the end of what we want to prove. So this final point lives in the target set. So for this trajectory, we can say, yes, that worked. But of course, this is really just for this initial point. So here I define some convenience function to plot this stuff in just one command. there's no magic going on. So now I do the same in the x3, x4 projection. So here we start there, and this is the trajectory, takes this loop, and in the end it returns. So, and you can see at the very end it really just returns. But still, it seems that this works, but this was, as I said, only one trajectory. So let's try a few more. So here I simulate for three random trajectories, and additionally I include all the vertices of the set, because usually the extremal behavior emerges from the vertices, but this is not, well, there's no proof for that, but it's a rule of thumb, I would say. So now we have in total 19 trajectories, and we can plot them all together, of course, and it looks like all of them indeed go to this target set. So it seems like we could try to prove this property. So let's try it. Here's the other projection, and it also works there. So now we do the reachability analysis. So, okay, I first add the plotting of a flow pipe to my convenience function, and then we start here. So again, I use this TM-JETS algorithm which we use for nonlinear systems. Then I use this AI squared algorithm for propagating through the neural network. I will not explain how this works, but this is implemented in this neural verification package. And then we just have an interface. Oh, it's not just, but we have an interface where you pass these two algorithms, and then it will just iterate through this loop, but in a non-trivial way. So it's not really just plugging these two things together. That's how we started, and it really doesn't work. So you need to know really the internals of these algorithms and plug them together in a nice way. And then we can, so what this takes, this includes, no, it's not much compilation time. This takes something like 2.5 minutes. Actually, it is faster when my CPU is not on full load. So I would say it should take something like 1 minute to compute this. But if we call the specification function, it will say that it is not proved. And if you can plot it here, the flow pipe, and you can see if you compare it to the simulation, it is, well, it's 2 cores, right? So at the end of this time horizon, we get to this set, which is not contained in the target set. So this does not mean that the property doesn't hold. It just means that our sufficient condition is not strong enough. In the other projection, it is actually working. So here we have this last small set, and this is contained. So the problem is in this projection. And since we don't really have time, I will just sketch the idea. So the real problem in reachability analysis is that you lose dependencies when you do this iteration through the loop and you go from one solver to the other. You tend to lose the dependencies of the different variables, and this just wraps up. So in this case, we did 50 iterations, I think, and yeah, it's really hard to preserve the dependencies for 50 iterations. So what you can do to mitigate this is to split the initial set into smaller sets and then solve many reachability problems. So in this case, we split it into 24 sets in total. And then we solve it for, well, actually the solve can take this splitter as an argument and do the splitting for you. And then, yeah, usually this takes 90 seconds on my computer. So after 90 seconds, you get a result that is more precise. So it's actually sufficient to prove the property. And yeah, that's basically what you can do at the moment. So as I said, the package is really new and it's still under development. And so for now, you can do simulations and set propagations for these control systems with neural networks.
Mm-hmm.
And yeah, that's it for this part.
I think the remarkable property that we should remark here is that while this flow pipe computation takes more time, then the result is fundamentally different from using simulations, because it can ensure that given the network that you have trained, you give the network to the system and the uncertain initial conditions, and then you have a proof that for any admissible initial condition, it is going to satisfy the property. So this is the kind of problem that we are solving here. There is also a question.
Yeah. Do you think one can auto-differentiate through the output of this verification? I'm not sure I fully understand this. So, no, I don't.
Well,
do you know?
This reminds me some ideas that we considered, in which we could go backwards in the loop, such as given there are some things we have tried, not that are related to propagating through the neural network, like backwards, in order to find, as the output of the algorithm. So for example, something we have tried is, if you give an output set, then find what, backwards reachable sets, which is a topic that has been studied for purely continuous systems. And so we are interested in computing backwards reachable sets for these classes of systems, which is more complicated because of the nature of the neural networks. But it is possible to do some things. So thanks. Thanks, Christian.
Thank you. So then we are done, and we did it in a remarkable 3 hours and 1 minute. Okay, so thanks everybody for attending, and yeah, hope to see to hear from you if you try the packages.
Thanks.